Hello, George Romanic here. Today we are going to talk about the Coriolis force in the distant past of our planet Earth. We are going back all the way to the Cambrian period, which was the first period in the Paleozoic Era, and that was some 538.8 million years ago from the present. Cambrian period lasted for approximately 53.4 million years. So as I said, started 538.8 million years ago. Cambrian period is the biggest explosion of life or of diversity of life on our planet. Before Cambrian period, we have the so-called Pre-Cambrian time. And during Pre-Cambrian time, which lasted basically between the formation of our planet some 4.5 billion years ago or so, up to 538.8 million years ago, there was either no life in the early stages of our planet, or research suggests if there was life close to the beginning of Paleozoic era, these were only some unicellular simple organisms. During the Cambrian period, there was a huge explosion of life. And many of the species that we have today started evolving back then. And during that time, planet was completely different compared to what we observe around us now. There was no life on the land. All life was in the oceans. And during, indeed, the Cambrian period, the first plants started growing outside of the water. Of course, during that time, we also have a very large continent above South Pole, Pannotia, and that continent started breaking apart, forming one very large super continent, Gondwana. And there were other smaller satellite continents such as Baltica, Siberia, and also Laurasia, which is, I believe, the foundation for today's North America. So that's a small, short history maybe about that time. So why is that time interesting? And why is it interesting? I mean, in the concept, in the connection to the Coriolis force. Well, back then, Earth was rotating faster. Earth was rotating faster, and that means Coriolis force was stronger than what we have today. And I will demonstrate in today's video how that affected wind systems or wind speed around the Earth. The text of today's problem is now on your screens. So first, let's remind ourselves for a split second, well, more than a split second, what is geostrophic wind? So if we have here, we are in the northern hemisphere, let's say we have P, pressure P here, and P minus delta P here. So there is this pressure gradient, and this is in the meridional direction, which means, let's say this is north, this is south, this is west, this is east. Then, of course, I have videos on geostrophic wind. Then geostrophic wind, Vg, blows parallel to the isobars, and we have pressure gradient force acting from high pressure to low pressure, and Coriolis force balancing pressure gradient force so that the wind is not crossing the isobars, but rather parcel of air is traveling parallel to the isobars. And what I said earlier, Coriolis force was stronger back in the days, in the Cambrian time, because Earth was rotating faster. So now we need to find this velocity Vg if the pressure gradient force is the same today and in the Cambrian time, well, first let's make sure that everything is here in SI units. So this is in degrees, that's fine. Delta P over delta N, 10 millibars over 500 kilometers. Let's put here this in the... Oh, by the way, delta N is this distance. This is delta N. Okay? Distance between P and P minus delta P isobars. So, delta P delta N, intensity of this pressure gradient, is equal 10 millibars. Well, that is 10 hectopascals over, millibar is the same as hectopascal, over 500 kilometers, and that's times 10 to power 3 meters. So this ends up being hectopascal is 10 times 10 to power 2 pascals. So 10 to power 2, that's 100 pascals, that's hectopascal, divided by 500 times 10 to power 3 meters. So this becomes power 3, and this power 3 cancels. So we get that this pressure gradient is 1 over 500 pascals per meter. I put units in the square bracket. And we will convert day into seconds when we calculate angular velocity of the Earth. Density of the air is assumed to be 1 kilogram per cubic meter. So now, Coriolis force, F Coriolis, is in intensity mass times Coriolis parameter times velocity, if we are interested in the intensity of the Coriolis force, okay? So it can be minus or plus depending on the component, but for the intensity we don't care about this. So that means that Coriolis acceleration in terms of the intensity is simply Fv. So we can see that acceleration caused by the Coriolis force is proportional to F and V. But F is Coriolis parameter, and that is 2 omega of the Earth, angular velocity of the Earth, sine phi, where phi is latitude. So you can see that this Coriolis parameter today is not the same compared to what it was during the Cambrian period, when one day was shorter. So let's calculate omega e for the present time, and then calculate omega e for the Cambrian time, and then we can calculate this Coriolis parameter for these two periods. So omega of the Earth for the present time, right now, today, is equal 1 full rotation of the Earth, which is 2 pi over 1 day today, and that's 24 hours. And 24 hours times 60 minutes times 60 seconds, you get this in SI units, and this is approximately 7.3 times 10 to power negative 5 second minus 1. So this is angular velocity of the Earth today. This is approximate over here. Now, angular velocity of the Earth during the Cambrian time, I will use subscript C, is equal, again, 2 pi, 1 full rotation, but not in 24 hours, but in 20 hours times 60 minutes times 60 seconds, That's how many seconds is in 20 hours, plus these 40 minutes, plus 40 minutes times 60 to get everything in seconds. And this is equal, I don't know now in my head, if I calculated this correctly, you can double check. This should be approximately 8.4 times 10 to power negative 5 second minus 1. So you can see that angular velocity of the Earth was larger in the Cambrian time than what it is right now today. Okay. So now we can go ahead and calculate Coriolis parameter. So Coriolis parameter F for the present today is then equal, so we plug in this over here, multiply by 2, take sine of 45 degrees, I would get that this is approximately 10 to power negative 4 second minus 1. This is Coriolis parameter today at the latitude 45 degrees north. Now, let us calculate Coriolis parameter during the Cambrian time C. So that would approximately be equal, I take this number, multiply by 2, take sine of 45 degrees, and because I didn't live in Cambrian time, I don't know this number like I knew for the present time. So this number, if you calculate it, should be 1.2 times 10 to power negative 4 second minus 1. So this is the Coriolis parameter some 538.8 million years ago, when we had explosion of life on this beautiful planet. Now, when we know this, we can go ahead and calculate geostrophic wind, because from my previous videos, you know that geostrophic wind intensity is equal 1 over rho F delta P delta N intensity. Well, so from here, if I calculate this for the present, Vg present is equal, rho is 1, F present is here, and delta P delta N is here. If I calculate this for today, I will get that this is approximately 20 meters per second. So geostrophic wind that corresponds to this pressure gradient and that latitude over there and that air density, and given the today's duration of the day, is 20 meters per second. Now, geostrophic wind during the Cambrian period will be, let me write it down now, so 1 over density is 1 times F for the Cambrian time is 1.2 times 10 to power negative 4, delta P delta N is 1 divided by 500, and if you calculate this, you will get approximately 16.7 meters per second. So, this geostrophic wind was weaker during the Cambrian period, some 538.8 million years ago, because Coriolis force was stronger. Now, let's try to understand why that makes sense. Well, we are fixing pressure gradient. So pressure gradient is the same 1 over 500 pascals per meter. Is the same today and during the Cambrian period. Okay, so there is this Coriolis force that needs to balance this pressure gradient. Now, Coriolis force depends on mass. We assume that mass of the parcel of air is the same today and back in the Cambrian time because densities are the same. So this is the same. Now, Coriolis force depends on F and depends on V. Because F in Cambrian time was larger than F today, look, then velocity can drop down and Coriolis force, thanks to larger F, will balance this pressure gradient. And that's how you explain the fact that geostrophic wind is weaker because Earth was rotating faster and the Coriolis parameter, that is therefore larger, enters here and can balance the pressure gradient force with smaller velocity, because Coriolis force depends on velocity. If there is no velocity, there is no Coriolis force. Of course, if you are really interested, the pressure gradient force, I didn't write it, but pressure gradient force is, in terms of intensity, is 1 over rho delta P delta N. I mean delta P delta N. This is pressure gradient force. This is Coriolis force. So you can see that pressure gradient force doesn't depend on velocity. The pressure gradient is the only thing that is driving this force, but the Coriolis force depends on velocity. But because Earth was rotating faster back in the days, velocity can drop down, and thanks to larger F, Coriolis force can still balance this pressure gradient force. Atmospheric sciences, climatology, paleoclimatology, physics, oceanography, and Coriolis force are absolutely beautiful. Until next video, goodbye.